Hello, welcome to today's video. Today we're going to be talking about compositional joint inversion in a laminated formation. So the first thing I want to do is go over what we mean by joint inversion. In general, we just say that we have some inputs, physical properties or weld logs. In most cases, people are familiar with using weld logs in UTAPWeLS because our main focus is modeling and for formation evaluation. We turn those logs into physical properties, what we call physical properties. But there is always a one-to-one relationship between weld log and a physical property that we can use as an input. It can be the gamma ray, the density, neutron porosity, resistivity, sonic, many other logs, NMR even. And then we combine all these through this joint inversion algorithm, this compositional joint inversion algorithm, to get the outputs, which is basically the interpretation, the weld interpretation, or what we call the petrophysical properties. So we're trying to understand what's going on in the subsurface, which includes the porosity, the water saturation, the mineral composition, and even the shale structure, which is something I believe exclusive to UTAPWeLS. I'm not completely positive about that, but it's something exclusive to modeling. So that's going to be important. To understand this, we need to understand the rock physics models. We call joint inversion because we're going in the inverse direction compared to the rock physics models. Rock physics models are any model that taking the composition, so the porosity, water saturation, and so on, can calculate these properties. So for all the nuclear properties, we could say, well, that's using the Crafts method, using UTNUPRO or other softwares. For density, it's just a weighted average. For gamma ray, it's just a weighted average. For resistivity in particular, which is going to be most interesting, in most cases, we just use Archie's model, and that's okay. But if we want to go a little deeper and we want to consider the effect of shale, like we should in most cases where we have shale formations, we need to use any of these models. And if we want to go even further and consider laminations, consider the structure of the shale, in most cases laminations, but it could also be laminar dispersed or laminar structural or either of those independently. But the one that makes it a little more interesting is when we have laminations. When you have laminations, the tool is reading either, well, you try to turn the tool readings into RH and RV. That's the first interpretation that we do. Getting those readings is beyond the scope of this video, but you understand what I'm talking about. And you know where to dig in if you're curious about that. RH is going to measure the resistivity of the formation, but because you have the laminations, it's going to be reading it like if it was a circuit in a parallel. So the resistivity for the part that is shale, the shale lamina, is going to be distinctly different from the lamina that is clean sand. In this purely laminar system, we have clean sand and pure shale alternating. In other cases, we're going to have different situations, but the point is that you're going to have alternated lamina with two distinctive resistivities. So RH is going to be reading that resistivity like if it was a circuit in parallel, and RV is going to be doing the same, but the circuit is now in series. So that's how you tell the difference between those two, and that's what the readings are telling you about the system. You can include that in the model, and that's what we've done in UTAPWeLS. And you're gonna use those two logs to get more information out of your weld logs. Now, we're gonna jump out of the presentation and go into UTAPWeLS. In UTAPWeLS, we have, assuming that you already have all those properties set up. So those are going to be the inputs, the bulk density. In this case, we're going to use bulk density, resistivity, perpendicular, resistivity, parallel, and we're going to use also, let's use gamma ray. So we're going to have these four properties. It could be the logs. There's methods to do this. There's other videos where we explain how to populate properties and things like that. So basically, we've turned logs into these properties. These are going to be our inputs. And then our outputs are going to be the porosity, the water saturation, shale concentration. The outputs are going to be strongly dependent on what we're understanding that we have. We can say we have clean matrix, pure shale, unstructured shale. We can say it's laminar. In our case, we know it's a laminar system. So we're just going to say it's laminar. We have the porosity. We have water saturation, shale concentration. And then for each one of them, you have the option to fix it to the model in case you have core data. You can fix it to the initial values in case you have populated that properly, or in case you believe that the initial value is not to be changed. And you need to define what the matrix, the fluid, and the shale components are. So you can go in here and you're going to get this window where you have the components for the shale. In this case, we're just going to say it's clean quartz, so it's sandstone. You could add any other components from here, but we're just not going to use them. We're just going to say it's quartz. The fraction is 1. You could fix it to fraction. This makes a little more sense than up here. You could just say it's a matrix that is 30% quartz and 70% calcite, or whatever you want to say. Or you can give it a minimum and a max if you want to constrain the results. Then you have the formula. This is going to be very important because this is how you calculate any of the nuclear properties. So for example, neutron porosity is being calculated using this formula. And then here it just shows you the total properties. So you just get an idea of what this is. If you want to, these are the properties that you could show. For example, you could also show photoelectric factor or any other properties, or less if you care about less properties. Then you can do this for the matrix. We can do the same thing for the shale. In our case, the shale is going to be just one component that we call shale that we have designed before. This is the formula. It's a bit complicated, but that's okay. You have the density. By the way, you can modify the density here. You can modify the gamma ray here if you want to give it a different value, and then that would be refracted down here. So if you wanted to say, well, it's not 2.78, it's 2.8, you just do that. The value is going to change, but we're going to set it back to where it was because that's the correct value. And now you can see how that is affected by the porosity. The synthetic case that we're working on has a shale porosity of 0.5, so 0.05, so 5%. And we're going to say it's fixed. You could allow the porosity to fluctuate. This is something that some users think is very convenient. The shale doesn't need to be 100% predefined. You can have a shale where the properties are varying a little bit. So you could have one that has some shale and another kaolinite or any other mineral you could have here, and then say, well, I don't want them to be fixed. I want them to be fluctuating. It could be that the shale is changing in composition in the interval of interest. That's something you can do here. And then you have the fluids, which in most cases for shale is just going to be water. But if you wanted to add something else, some people add not just other hydrocarbons, but you can have carbon dioxide. You can have some people include ions and different things. For now, we're just going to say it's water. This is good. And then you have the fluid. Those are the 3 main components that you need to define. And in our case, it's just methane, and we're happy with all this. Fine. So now that we've defined the outputs that we're interested in, we have some formation conditions. You can take them either from the Earth model if you've populated them already, but you can also say, well, I want it to be, whatever other value, 180 or whatever other value, and you have the units right here, so it's easy. And in some cases, people have used it also for testing different hypotheses if they're not quite sure about the pressure. So how is that pressure going to affect the inversion? You can see that here. Of course, the fluids are the air is the part that is going to be affected the most by pressure, or salinity is one of the big ones. You can do it even when you have some invasion, and you can estimate uncertainty. So in this panel we have the method settings where it allows you to consider invasion. If you have done a piston-like invasion modeling in the past, there's other videos to explain that in a little more detail. That can be considered. Right now we're just focusing in laminations. And you can estimate uncertainty. These are other settings for the method. This is the number of points that is going to help you estimate the uncertainty. 50 is a good number. You can make it higher if you want more resolution. This number of iterations is for the inversion algorithm. The same thing with the step tolerance. By default is 1 times 10 to the minus 8. That's what this means. And it's a good value. Sometimes you need to make it a little smaller. Sometimes you can make it faster by making it a little larger. This is the the parameter that has the highest impact in that trade-off between accuracy and time. So it's up to you to decide what to use. Oh, and I forgot here, information conditions. You can also, you're going to be using water resistivity if you have a resistivity property here as an input. So just because the resistivity model is going to include it. So you can either calculate it from the salinity that you have, if you check this, or just take whatever the previously calculated value was. All right. Then it's going to open some diagnostic plots. You can calculate hydrocarbon pore thickness and calculate permeability, and so on. So I'm going to let it run, and I'm going to talk to you about the specifics of this model that we're working. Oh, well, actually, before I go into that, up here we have some other databases. We have the rock class, which tells you exactly what is being used for any of these properties, how they're being calculated. So it's basically the rock physics model. So for nuclear properties, there's not a lot of wiggle room. For resistivity, we have this button that shows you what are we using. So you can use for the rock class default. Actually, this should be Juhas, so I'm glad I opened it. We're using Juhas and tells you what are the parameters. We're just leaving everything in default. In Juhas, you consider the water resistivity for the shale. So it's a value that we're going to assume this is correct. You have the laminations and anisotropy. So these are the resistivity of the lamina for shale as a explicit value, and it can be anisotropic. We're just going to say it's 3 and 3, so it's not anisotropic, really. And this is also just when you're calculating water saturation, you can do it from RV or from RH or from both and just take an average. This is what this is telling you. And whether you want to make sure that structure is consistent with all the properties. And that is just whether it's laminar or whatever, and making sure that the 4 parameters that go into the Thomas-Tiver diagram, meaning shale concentration, total porosity, shale porosity, and matrix porosity or clean sand porosity, this goes by many names, are consistent with each other. And if that is, if you're using some laminations, you want to make sure that it's enforced. So it's good to keep this checked in. All right. Now that we have this, we have the right resistivity model. For the nuclear properties, like I said, we just use UTNUPRO and it's fine. Or for gamma ray and for bulk density, actually, they're just weighted averages and that's okay. And I'm just going to let it run. And we're going to see what the model that we're actually inverting for looks like. And we're going to see here it is. So it already has the results from the previous inversion, but this is what the model looks like. Actually, let's go to this other template where we have the original inputs. And so we have the shale concentration, which is right here. It was designed so that you would have, so here in the composition plot, you can see we have in the top, we have pure matrix. So the yellow is just quartz, shale here, water associated to shale, here a little darker blue. Then in green, we have methane, and then water that is not associated to shale further out. You can see it's a very smooth transition from pure matrix from clean matrix to pure shale. You can see a shale concentration going from 0 to 1. The porosity is going from higher to lower, just following that same trend. And the water saturation has that follows that curve. If you use these properties as inputs, you get this. The true is the input. You can calculate density, gamma ray, and the resistivities. Because it's laminated, you can see the RH and RV, how they're going. You see this anisotropy. It's a very nice plot. Clearly, what we're interested in seeing, and we're just gonna let it run, and by the end of it, it's now layer 23 out of 30. By the end of it, it's just going to modify these plots slightly, and it's also going to open the diagnostic plots, which are going to be interesting for deciding whether the inversion is correct or not, even if we're not working with a synthetic model. This is a synthetic model, so we can know exactly how good we are. But if you're in real cases, you don't know the true properties, of course. So indirectly, we're gonna assess how accurate the inversion was, and we do that by comparing the properties that we are giving as inputs, so density, gamma ray, and resistivity, and I didn't mean to move this plot, so we don't move it, to the proposed properties. So these are the plots. These are the diagnostic plots. And you can see that they are basically on top of each other, which means that we are getting a very, very good result. All the plots are almost exactly on top of each other. You can see minor variations in some of the numbers, but basically it's an exact match, which is what we expected in a way, because we have the shale concentration, the water saturation, and the total porosity as 3 variables, and we're giving 3 inputs. So it's an overdetermined case, an ideal overdetermined case, which we should really be able to get everything perfectly fine. And that's what we're saying. So this is good. Now I'm going to show you some other results of not so perfect, which is something you want to see to really understand how the system is going to work. So this finished. It took 2 minutes and 21 seconds to run 30 layers, just to give you an idea of what to expect if you're running, depending on how many layers you're running. Anyway, so these are the results that we are getting. They're fantastic because we're in an ideal world where we're having everything together. So that's great. Now we're back in the presentation. These are the results that you saw. Now we're gonna see other cases. The case that you just saw was case number 1, where the shale structure was laminated, which is accurate from the synthetic model in the forward case. The input properties were all the possible properties, so we have 4. Now we're going to decrease that. We're going to get rid of gamma ray in the first case. So this should be 3 to 3. We should see the same thing, but probably a little less accurate. And more importantly, the uncertainty is going to be a little wider. And something similar we're going to see in case number 3. We have the same, except we're replacing, we're bringing gamma ray back in, and we're getting rid of RV. So we still have three values, 3 properties in, and we're trying to see what can we get. And then in the last one, we have a case just to see a reference of in case we do not consider the shale structure. So it's basically the wrong physics. So of course we're going to get the wrong answer, but it's interesting to see. Anyway, so now we can see these are the results that we saw before. You can see how the match is pretty much perfect between the inverted. In red, we have the inverted shale concentration, and in blue dotted lines, we have the true values for shale concentration, porosity, water saturation. It's pretty much a perfect match. You can see the uncertainty, and there's a couple of cases where the uncertainty is bigger than we would like, but it's not terrible. It's always water saturation, which is hard because of the logarithmic scale for resistivity, but it's okay. It's something we can work with. And here we have the hydrocarbon pore thickness, where you see the uncertainty is getting a little bigger as we go. It's cumulative, by the way. It's starting the bottom and then it's growing towards the top. It's just how many meters do we have? How many meters of effective hydrocarbon do we have in this area? And that's fine. Now, case number 2, we can clearly see that the biggest difference is not that we're getting worse match, but the uncertainties are bigger. And it's where we're just using 3 inputs instead of 4. But we still get pretty much perfect results with higher uncertainty. The uncertainty, again, it's not so smooth. We have higher uncertainty everywhere. Something very similar happens when we get rid of gamma ray, even higher uncertainty, which is fine, but the results are still pretty accurate. And then we have the one where the physics are wrong, so the answer is clearly wrong. Especially in the shale concentration, we can see the shale concentration is completely off. If you remember, the plots in the other ones were completely different, so we're not getting the right answer. We should not expect the right results anywhere. Anyway, so that's just to give you an idea, to stress that if you have a laminated system, you should use laminated physics. That's the point of this plot. And to finalize, just a summary of the results, just how big was the error for the CSH, case 1, 2, and 3. Just case 3 is the only one that has meaningful errors in CSH, porosity, water saturation, and the cumulative hydrocarbon pore thickness. They all have, well, except case number 1, which was very, very ideal, they all have certain error, but of course this one is much bigger. In these two have some error that is not too big, just to put it out there. And with uncertainty, it's interesting. We clearly see that the mean uncertainty is bigger as we go progressing in the cases, that we're getting less ideal as we go out, or as we increase the number. The uncertainty gets bigger in all cases. It's particularly big in the case that had the wrong physics, which is what we want to see. Interestingly here, this is the cumulative pore thickness, hydrocarbon pore thickness. So it doesn't mean that the total uncertainty is smaller. We see that the case number 4 has smaller. It doesn't mean that overall it's smaller. It just means that had errors up and errors down, that at the end they were smaller. In the cumulative, they were smaller than the others. But don't be deceived by that. That's just the having many negative and many positive errors doesn't mean that the total error was not bad enough. It's the assessment is still pretty bad. Anyway, so that's what I wanted to show you. And just to wrap this up, just wanted to show you the results that we have, and stress that when we are dealing with laminations, you really want to take into account laminations. After you've evaluated not just the porosity and so on, you can also evaluate the permeability, and the permeability is going to be completely different when you have laminations and when you do not. So you want to be able to get the shale structure right if you want to do good analysis. All right. Well, thank you. I hope people get some benefit out of this and use UTAPWeLS. Let me know if you have any questions and if you want to talk about anything else in particular. Thank you.